All right, Chapter 4, Part B. So I've cut Chapter 4 into 3 different lectures. Last lecture, Part A, we focused on compounds that are held together by ionic bonds. So if you recall, ionic bonds happen between a cation and an anion. Most often a metal and a nonmetal are going to form the ionic compounds. Today we're going to talk about covalent compounds, which are also called molecular compounds. So once again, looking at our flow chart, matter is broken up into mixtures and pure substances. Pure substances is further broken down into elements and compounds. And then here's where we are with Chapter 4, where compounds are broken up into 2 categories, either your ionic compounds or the molecular compounds. So the next 2 videos are going to focus on the molecular compounds. So if we look at the electron dot structure for chlorine, so do you recall that electron dot structures, you put valence electrons as dots. So chlorine is in the 7A family, so it has 7 dots around it representing those 7 valence electrons. If you look at chlorine, it has this unpaired electron. So it is a highly reactive particle. It is looking for another electron because it wants to reach its octet, right? So this electrically neutral atom, the chlorine, with an unpaired electron is what's called a free radical. So I do want you to memorize that. When you have an atom or a molecule that has an unpaired electron, that is called a free radical. It's much too reactive to exist very long alone by itself, so one of the things that it does is it combines with another chlorine atom to form this Cl2 molecule. So other elements that behave this way are known as what we call the diatomic elements. There's 7 of them, and I want you to memorize them. So the diatomic elements are Honkelbrief. So this is an acronym we use to help students remember the 7 diatomic elements. So hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So I do want you to memorize those 7. When you write them down, when I teach you chemical reactions and you go and you write down, so say I say chlorine reacts with sodium, I expect you to write down chlorine as Cl2. Okay? If I wanted just a chlorine by itself, I would have to specify that it's a monatomic chlorine. If I don't say monatomic chlorine, then you are to assume that it's diatomic and write it down as Cl2. So how is it that this chlorine molecule is held together? So if we look at ionic compounds like we did last chapter, let's focus on that. If we've got the 2 chlorines, and remember when an ionic molecule is formed, one of the elements steals an electron from the other element, making a cation and an anion. So does this seem to be a logical explanation for chlorine? So let's go ahead and look at that. Here are my kind of a schematic showing the electrons around the chlorine atoms. So I'm starting off with 2 neutral chlorine atoms. Once again, they're called free radicals. And I'm showing the 7 valence electrons on each one. So remember, they're all trying to reach an octet. So does it make sense to you that this chlorine atom is going to pluck one of these electrons off this chlorine atom? I mean, it's true, if that happened, they would stick together because this chlorine would become an anion and this chlorine would become a cation. But I hope it doesn't make sense to you. This chlorine is not going to want to lose an electron because, one, it's a nonmetal. And remember, nonmetals have high ionization energies. As you move from left to right and bottom to top on the periodic table, your ionization energy increases. So it's harder, it takes more energy to take an electron away. So this scenario is not going to be a good explanation for how 2 chlorine atoms stick together. Here is another explanation, and that is they're going to share electrons. So if these 2 chlorines move closer together and share these 2 electrons, in as much as each one then can feel those 2, then it's gonna appear to each chlorine that it has its octet, because both chlorines take part in these shared electrons. So shared electrons are called the bonding electrons. So these 2 electrons here in the center being shared by both chlorines are the bonding electrons. The unshared electrons are called non-bonding electrons. So all these electron pairs around the outside that are not being shared are called non-bonding. I have another word for those. Let me get my pointer. That I'd like you to write down because I tend to use this word most often. There we go. Non-bonding electrons are also called lone pair electrons. So I use both of these words, so go ahead and memorize those. A covalent bond is one that is formed by the sharing of electrons. Both atoms, which are usually a nonmetal to a nonmetal, wind up with an octet of valence electrons then. Electrically neutral groups of atoms held together by covalent bond are called molecules. Or, I should probably say here, molecules or compounds, or covalent compounds. So if you say covalent compounds, then I know you're talking about a molecule. The atoms in a covalent compound are held together by covalent bonds. So some physical properties of molecular compounds. So I've got a couple examples here for you, 3 of them actually. And if you notice, they all have nonmetals. Carbon is a nonmetal, hydrogen's a nonmetal, even though, remember, hydrogen's an exception. Even though it's on the left side of the stair step, and so you might think it's a metal, it's not. Hydrogen is a nonmetal. And oxygen's a nonmetal. So once you notice that all you have is nonmetals, then that's going to imply that it's a covalent compound. Same thing with water and carbon dioxide. Chemical combination of nonmetals with other nonmetals. They're going to exist as solids, liquids, and gases at room temperature. So we're going to compare and contrast covalent compounds with ionic compounds. So if you remember, ionic compounds tend to be solids at room temperature, where covalent compounds can be all 3 states of matter. I mean, if you look at the 3 examples I have up here, the first one here is a sugar, and it's solid at room temperature. Water is a liquid, and carbon dioxide is a gas. They tend to have low melting points, and that's relatively low compared to ionic compounds. They have low boiling points compared to ionic compounds, and they're often insoluble in water, where we're kind of familiar with salts. Ionic compounds often being soluble in water, covalent compounds often are not. Okay, so how do we name covalent compounds? The first step is you're going to name the first nonmetal as the element. So you don't tweak the name at all, just write it down exactly like you find it on the periodic table. And you're going to use the prefix if there are 2 or more atoms. So these Greek prefixes are on your information sheet. They're to the left of the polyatomic ions that we worked with on the last lecture. So we're giving you the Greek prefixes, but you need to remember to use them when you are naming a nonmetal bonded to a nonmetal. Okay, so, but it's a little tricky on the first one. If you only have one, the prefix for one is mono. So you usually would put the prefix mono if you have one of them. But on the first element, you don't use the prefix mono. That's why it's saying right here 2 or more. So use a Greek prefix if you have 2 or more of the first element. Step 2, you're going to name the second nonmetal, changing the ending to "ide." And here you're going to use a Greek prefix all the time. So even if you have one, you're going to use mono. If you have 2 of them, you're going to use di. So let's do a couple examples to go through this. So write the name of each of the covalent compounds. Okay, so I've got 1 carbon here. So we would want to say monocarbon, but we drop mono if it's on the first one. So we're just going to say carbon. The second one we only have 1 of, so now we're going to put down the mono. And the name of this is oxygen, but we're going to change it to oxide. Now, there's really no real hard, fast rules for me to teach you about when to drop a vowel. So I'm not going to deduct points if you fail to drop a vowel. But if I was to write monoxide, notice that there's 2 O's together. So often they just drop one of the O's and just come up with monoxide. So that one's carbon monoxide. Here, when we go to name the second one, we only have 1 carbon, so we're just going to say carbon. And now we've got 2 oxygens. So you go to your Greek prefixes and you look up the Greek prefix for 2, and that is di. And this is oxygen, but we're going to change it to oxide. Okay, the next one, I've got 1 phosphorus, so I'm just going to say phosphorus. And I've got 3 chlorine. So you look up the Greek prefix for 3, and that is tri. And chlorine is going to change into chloride. Notice they're all ending with IDE. That's going to be your only ending for covalent compounds. When we were dealing with ionic compounds, remember we had to worry about whether it was going to end with ide, ite, or ate. Well, for molecular compounds, they're just all going to end with ide. Going on to the fourth one, I only see one carbon, so I'm just going to write down carbon. But I see 4 chlorines. So I look up the Greek prefix for 4, and that is tetra. And then chlorine is going to change to chloride. Okay, this next example. The first element is nitrogen, but now I've got 2 nitrogens. So I do have to put a prefix on this first one. You're always going to have a prefix on the first one, except if you only have one of them. So this is dinitrogen, to let the reader know that you've got 2 nitrogens. And I only have 1 oxygen, so I'm going to say monoxide. Okay, but once again, I want to remind you that when I ask you to name a compound or write a formula, the first thing you want to do is decide whether it is an ionic compound or a covalent compound. Okay, that's always your first question because there's 2 different sets of naming rules, so you want to make sure you have that straight. So here's a learning check. Write the correct formula for each of the following. So pause the video and see if you can get these right. No Greek prefix on my first word, so that must mean there's only one of them. So there's 1 phosphoruses, and penta means 5, so there must be 5 chlorines. So 1 phosphorus and 5 chlorines. Here, the di means 2, so I've got 2 nitrogens. 2 nitrogens. Tri means 3, so I have 3 oxygens. Okay, come down to the third one. There's no prefix on the sulfur, so that just must mean there's 1 sulfur. And hexa is the Greek prefix for 6, so there are 6 fluorine atoms. Okay, Lewis structures. In this class, I'm not going to teach you how to draw Lewis structures, but I am going to be giving you the Lewis structure, and I'm going to expect you to be able to get a bit of information from looking at the Lewis structure. So Lewis structures are also called electron dot structures. They show how the valence electrons are arranged around the atoms in a molecule, and to explain the chemical bond formation. So remember that hydrogen's an exception, and hydrogen's octet is 2 electrons. So when these 2 hydrogens share, they each have 1 valence electron, so they come together to share their individual one, and here they have 2, so that satisfies hydrogen's octet. We talked about chlorine. When it shares its lone electron, then both of those chlorines fill an octet. When you're drawing a Lewis structure, we tend to show these shared electrons represented as just a line between the 2 atoms. So the first thing you want to memorize is that one line represents 2 electrons. Okay. The lines, those 2 shared electrons, are called the bonding electrons, or those shared electron pairs. And the electrons out here that are not part of the bond are called the non-bonding electrons, or lone pair electrons. Okay, so those are Lewis structures. So I've got a couple of them here for you to look at. I want you to think about, what do all of these molecules have in common? This is a pretty important step when you're drawing Lewis structures. So what I'd like you to see is that all of the elements have their octet met in a Lewis structure. So if we focus, remember, every element wants 8 except hydrogen and helium. They only have that one shell, that first shell, and so it can only hold 2 electrons, the 1s2 shell. So carbon, if we look at it, I'd like you to be able to tell me that it's got 4 electrons surrounding it, because each one of these lines represents 2 electrons. So this carbon is filling 8 electrons, and each one of these hydrogens is filling 2 electrons. So they all have their octets met. If we look at this one right here, the sulfur is filling 8 electrons. It's got 2, 4, 6, 8. So sulfur is happy it's got its octet. Oxygen is filling 8 because it's got the 3 lone pairs and then the bonding pair. So in drawing a Lewis structure, all the elements are going to share electrons to achieve their octet. Okay, so I'm going to be giving you the Lewis structures, but one of the things I'm expecting you to get by looking at a Lewis structure is what's called the Vesper geometry. and then the shape of the molecule and the bond angles of the molecules, okay? So a little bit about the shapes of molecules. There is something called the VSEPR theory. In the valence shell electron pair repulsion theory, and that's where we come up with the VSEPR. Notice I say VSEPR, but it's not actually spelt out like VSEPR. So we know that we pronounce it as if the E and the S is traded places, but we know it's not. So that stands for valence shell electron pair repulsion. So in this theory, the electron groups around that central atom are arranged as far apart from each other as possible. So hopefully that makes sense. Let me go back to this slide. We know that electrons have a negative charge, and like charges repel each other. So does it make sense that the two electrons in this bond are going to repel the two electrons in this bond? They are going to try to get as far away from each other as they can. So that's really the main premise for the valence electron pair repulsion theory, is those valence shells around the central atom are going to try to repel each other as far as they can. Those valence electrons will have the least amount of repulsion of the negatively charged electrons. They're going to have a geometry around that central atom that determines the molecular shape. Okay, so we're going to first think about our electrons, those pairs of electrons around the central atom, and where they end up to minimize the amount of repulsion, and then that's going to lead to what shape the molecule is. This slide takes us through the three different electron shapes we're going to deal with in this class. So there's two different categories I'm going to teach you. I'm going to teach you how to tell the shape that the electrons are in, and then we're going to switch to where you can tell me the shape that the actual molecule is in. So this slide is dealing with the shape of the electrons. So that's why it's called the electron group geometry right here. This geometry is also called, so you might want to write this down on your notes, the VSEPR geometry. Valence shell electron pair repulsion geometry, or geometry or shape. Those words are interchangeable. So I might ask you the VSEPR geometry or the electron group geometry. And what I'm asking for there is what shape are the electrons in. So if you look at this VSEPR word, that central E there is representing the electrons, okay? So we're only going to deal with 3 electron shapes in this class. And if you think about them, I've got this central atom here. The shape is always determined around a central atom. And I've got my lone electrons on these lines. So let's kind of think about these lines as being a string. If I charge these 2 strings with both of them with negative charge, and they're going to try to repel each other, they want to get as far away from each other as they can. And the farthest 2 groups can get away from each other is 180 degrees. And we would call that a linear electron shape. Here, if I've got 3 electron groups around my central atom, so here's my central atom, I've got 3 electron groups around it. The farthest 3 groups can get away from each other is 120 degrees. And we call that planar triangle. Actually, I think your book is calling it trigonal planar. I'm going to write this down. Because when you're doing your homework, I think it'd be best to memorize the way your book is doing it. So when you're doing your homework and you're typing it in, if the software is picky about that, then you'll be plugging it in that way. So, but notice, either way is fine with me on a test or a lab or something like that, because both of them are conveying to me that you know it's planar and you know it has a triangle shape. So trigonal, planar, planar, triangle, however you want to do that. I've got a picture of that one here. So we're going to come back to these models. I put together a linear one. So we'll start with the linear one. When you're doing your kits, because we're going to do this in lab, if a molecule has got a double bond, you're going to use 2 of these gray sticks. So these are just representing a double bond, and it's going to be important that you know to count your double and triple bonds as one group. So this carbon has 2 groups of electrons. It's got a group to your right and a group to the left. So these 2 electron groups are going to lead to 120 degree or 180 degree angle. So notice my lines all line up in a linear shape. The trigonal planar the bond angles are 120. And they get the word planar because if you look at this, they all line in the same plane. I'm not sure how well you can see that from your angle, but I can dissect these along a plane. So that's where they get the name planar triangle, because it makes the shape of a triangle. The fourth group is called a tetrahedral. So when you've got 4 electron groups around your central atom. So here is an example of that. My black ball, the carbon, is my central atom. And I've got, now remember, at this stage of the game, we're not looking at the atoms, we're looking at the electron groups. So we're looking at these gray bars. This carbon has got 4 electron groups. And it turns out that the farthest 4 electron groups can get away from each other is 109 degrees. So you're going to want to memorize that. Okay, I've got that on the chart, 109 degrees. And this shape is called a tetrahedral shape. One main thing I want you to notice, and I don't know if you'll be able to notice it if I hold it up, but there's air underneath here. There's nothing planar about this molecule. Okay, these legs are kind of coming down like the legs of a tripod. So that is a tetrahedral shape. It would be wise to kind of memorize that shape. So when you see 4 electron groups, think, that's tetrahedral. 3 electron groups is going to be your trigonal planar, and 2 electron groups is linear. So those are the only electron group geometries you need to memorize for Chemistry 103. Okay, so a guide to predicting the molecular shape. So now I'm not talking about the shape of the electrons, I'm talking about the shape of the molecule. Okay, using Vesper theory, don't let that throw you off, because often the test questions say, using Vesper theory, what is the molecular shape? Okay, that is not asking you for the Vesper geometry that we just went over. It's asking you for the molecular shape, which I'm about to teach you. But they often say using Vesper theory. Okay, so from the correct Lewis structure, which I'm going to try to give you all the time, use the number of atoms and the non-bonded pairs directly attached to the central atom to determine the electron geometry. So your first step is to determine that Vesper geometry. Okay, that's going to help you then determine the shape of the molecule. So your first step is to determine the electron pair or electron group geometry. And remember, there's only 3 you have to memorize in this class: either linear, your book's calling it trigonal planar, or tetrahedral. Okay, so first decide whether the electron pair geometry is linear, triangular, or tetrahedral. Then the shape of the molecule is what you can observe with technology. So basically you pretend you're looking through a microscope, and you pretend that your microscope does not have the ability to see electrons, but it does have the ability to see atoms. Okay, so you're trying to figure out what is the shape of your molecule through your microscope that cannot see these electrons. Okay, so to determine the shape, place the atoms into the previously determined electron geometry and see what's left. So let me try to explain. Okay, so we're going to start off with focusing on if there's 4 electron groups around the central atom. So I'm going to take you back to the tetrahedral shape. Okay, so the first step is determine the electron pair geometry. So that means we're looking at the electron pairs. So in this example, I've got 4 electron pairs and 4 surrounding atoms. So if we look at our chart, this is the first row in my table here. I've got 4 electron groups. Oh, let me grab my pen. Okay, 4 electron groups, that's my gray bars. I've got 4 atoms, that's the green atoms. In this particular case, I'm not going to have any lone pair electrons. And we know the bond angle is 109 because the bond angle always comes from the electron groups. So if I've got 4 electron groups, the bond angle will be 109. But notice this table has them all 109 because they all have 4 electron groups. Okay. So the shape of this, you guys would say it's tetrahedral. Now notice this is the molecular shape. So the Vesper geometry or the electron group geometry is tetrahedral, and the molecular shape is tetrahedral. So you're going to have to be able to, I'm going to give you a Lewis structure, and you're going to have to be able to tell me the Vesper geometry and the molecular shape. In this particular case, they're both the same. They're both tetrahedral. Okay, and that was my CH4. If I put together with my model kit NH3, my colors aren't going to match, but what you have there, let me draw out the Lewis structure for NH3. So I would have a nitrogen, this is what the Lewis structure would look like that I would give you. So 3 hydrogens and a lone pair here, because remember, nitrogen's got to have its octet. So do you agree that there's 8 electrons surrounding this nitrogen? 2, 4, 6, 8. So nitrogen's happy, it's got 8, and hydrogen only wants 2 electrons, so they're happy. So here's the Lewis structure for ammonia. Here's the picture it over here. So if I was to put that together with the model kit, I would not have that one atom up here, but it still has the lone electron pairs. So notice on the Lewis structure right here, this non-bonded electrons, running off the page, are still up here. But remember, to determine the molecular shape, we cannot see the electrons. So for looking through our microscope, we can't see those lone electrons, so I'm going to take them off. And then you need to come up with what a name for this shape is, because this is what you would see through the microscope. Well, what scientists have decided to name this is a pyramid shape, because it's kind of hard to tell, I'm sure, but it looks like a triangular pyramid. So that's where they get the pyramid shape. So on a test, you would tell me that this has a tetrahedral Vesper geometry, because the Vesper geometry is how many electron groups. Tetrahedral Vesper geometry, but the molecular shape is pyramid. Okay. What happens if we've got 4 electron groups and 2 bonded atoms? So water would be an example of that one. So let me draw you the Lewis structure for water. My central atom needs to have 4 electron groups around it. So, do you agree? 4 electron groups, because my lone electron pairs count as one group, and my bonds count as one group. So I've got 4 electron groups around this oxygen, but only 2 atoms bonded to this oxygen. So this falls into my 3rd row. So if I was to show us that, we would have a molecule similar to this, where I have still 4 electron groups. So the bond angles are still 109 degrees, but we're going to look through this through a microscope that cannot see these lone electron pairs, and scientists have decided to call this shape bent. Okay, so when I give you this molecule right here on a test, and I ask you what is the valence shell electron pair repulsion geometry, you're going to tell me that it's tetrahedral. So remember, you only have, when I ask you for the Vesper geometry, you only have 3 choices: linear, trigonal planar, or tetrahedral. But if I ask you for the molecular shape or the molecular geometry, you're going to say, I've got 4 electron groups, but there's only 2 atoms. So when you've got 4 electron groups, think about a tetrahedral in your head, and then think about what that looks like if you take off 2 electrons, and that's going to lead you to a bent molecule. And if I ask you the bond angle, you're always going to say 109 if you've got 4 electron groups around that central atom. Okay, let's go to where if we have got 3 electron groups. So starting off with sulfur trioxide, if we look at the Lewis structure down here, because this is what I'm most likely going to do, is give you the Lewis structure. So here's the Lewis structure of sulfur trioxide. I have put together that with the model kit. So here's my oxygen with the double bond, and my other oxygens with a single bond. And there is 3 electron groups, because double bonds count the same as a single bond. So you would look at this sulfur and say, here's 1 electron group, here's an electron group, and here's an electron group. So 3 electron groups is going to lead you to a Vesper geometry that is trigonal planar. Okay, and I'm simplifying it just as triangle. So if I'm looking at the molecular shape, I want to say 3 electron groups, 3 atoms. My shape is also trigonal planar. Okay. What happens if I have 3 electron groups but only 2 atoms? So an example of that would be sulfur dioxide. And do you agree that there's 3 electron groups? 1, 2, 3 electron groups. So once again, the Vesper geometry is trigonal planar. But that's not the shape we would see through the microscope. So this is what we have. We still have the 3 electron groups, but our microscope cannot see that lone pair electron. And so once again, this leads us to a bent molecule. But in this case, the bent molecule is 120 degrees apart, where in the last one, since there was 4 electron groups, the bond angle was 109. So you have to be very careful when you're recording that the shape is bent, because you have a bent with a bond angle of 109, bent with a bond angle of 120. Okay. And then we're down to 2 electron groups, and that's the easiest, because if you have 2 electron groups, you're always going to have 2 atoms, so that's always going to be linear. So you're always going to be writing down the word linear twice. The Vesper geometry is linear, and the molecular shape is linear. And the bond angle on something linear is 180. So here's an example of that. So you'd want to be able to look at carbon. The biggest mistake here is that students will say, oh, there's 4 electron groups around carbon. But you want to remember to count your single bonds, double bonds, and triple bonds as just one group. So I've only got 2 electron groups around the carbon.